I'm John Todd from Caltech. I have the pleasure of being chairman for this afternoon session. The first speaker, unusual to have a president of a university giving a technical talk. Dr. Booth from Lakefield University in Canada is going to tell us about computing in the University of London.
Well, thank you very much, Mr. Chairman. I just correct the program. I don't know where you got it from, but it's actually Lakehead University. And should say Lakehead. That's the program. I'm not responsible for it. I could, of course, read the script that I prepared for this talk, but I don't think I will. I'll give you a fair warning. Last year, before I gave the convocation speech, I was lining up in the lineup at our university. I heard one of my colleagues saying to another one, is he ad-libbing or has he got a script? And they didn't know, and they then started to take bets as to whether they'd be there for the whole afternoon or whether it was going to be a short performance. I could, of course, use the script, in which case it would be a reasonably short performance, but I'm not going to, but I'll still try to keep it fairly short. I'm reminded, of course, of a man whose name has not been mentioned, at least while I've been at the meetings this time, Norbert Weiner, who is often thought of as being interested in computing. Years ago, he visited my lab in London, where he was a friend of the late Desmond Bernal, and his talk was supposed to be on the human use of computing machines. And we showed the machine that we had to him. He looked at it and said, but that is hardware. And that offended the engineers. And then he came to lunch with Bernal, and Bernal, who was introducing him, said, well, what are you going to talk about, Norbert? Norbert told him, and Bernal said, but that's all wrong. You've got your Industrial Revolution totally wrong. And they had a bit of a confrontation over it, the result of which was that Norbert Weiner was persuaded that he was wrong. When he gave his talk, he talked for 35 minutes instead of 1 hour. And at the end of it, he came out, having had a rather hard time in the question period from the engineers who he defended in the morning. He came to my office and he said, isn't it remarkable how we academics can judge the exact hour? It was an interesting sidelight. Norbert, I don't think, had much practical influence on computers, but he was certainly a vocal gentleman. I thought that following the directive that we were given by Metropolis this morning over breakfast, that I'd make a few remarks which have been made during the conference before I start on my display of ancient pictures. I do this because I didn't do it in the discussion. I thought the times for discussions were rather limited and I shouldn't get up and be verbose. But I do have a few remarks which I think might interest you and might be apposite to the record. One of them concerns the early history of the differential analyzer. The first one of which I was aware was the Douglas-Hartree model made at Manchester around 1934. And my interest in that arises from the fact that the research student who worked with Hartree and whom I understand got his PhD for this project was Arthur Porter. Arthur Porter was at Manchester, later Professor of Light Electrical Engineering at Imperial College London. He then went to be Dean of Engineering at Saskatchewan for a variety of reasons, and I followed him very shortly afterwards. Arthur is now in Ontario, where I'm also in Ontario. He was Professor of Industrial Engineering at the University of Toronto, but he is now Commissioner for Energy for Ontario. So there's really quite a connection between the differential analyzer and the goings-on in Canada, and to that extent in the United States. There's another interesting sidelight about Arthur's activities. I don't think we have a representative from them here today, but Arthur Porter, in the Canadian part of his career, was concerned with Ferranti-Packard, who produced the FP6000. I think it was a one-of type job, but it is now at the Saskatchewan Power Corporation's laboratories, and it was one of the first machines, I understand, I know nothing about it structurally, to have to do with virtual programming. Arthur always maintains that that was where virtual programming was invented, and that was over 10 years ago. There were remarks made by various people about the origins of digital computing at MIT. I have one observation which may be of interest. I met in 1946 with Bush and with Caldwell. Vannevar Bush was another friend of my then boss's, Desmond Bernal, and talked to both of them about the prospects of digital computation. It wasn't mentioned, at least in my hearing, that the big differential analyzer at MIT in the 46 period of time was a card-programmed one. It had digital input. In conversations with Caldwell at that time, Caldwell made the point rather strongly that he believed that the solution of things like differential equations, which were continuous variable problems, were better accomplished by analog means with digital input to obtain whatever accuracy you wanted, rather than by discretizing, having all of the problems of convergence and so on, which we were hearing about this morning, and doing the thing digitally. Now, whether that throws any light on whether MIT would have produced the first digital computer or not, I don't know, but I offer it to you as an observation. There were other attempts at digital work which haven't been mentioned here, and there were other pioneers. Two of them were old friends of mine. I'm pleased to say they're both still alive. They were Charlie Beavers and Harry Lipson. Beavers and Lipson invented a method of Fourier transform generation in the 1930s and produced, between 1938 and 1944, a digital Fourier transformer. And in fact, that was one of the mainsprings of my own ideas in the X-ray field at that time. And there are papers on this subject, which I'd be happy to give references to. In fact, I think one of them is in the written version of this talk. It's the paper by Beavers and McEwen. We heard also in one of the same talks about the conjugate gradient method, which I had something to do with in its early days, but one of the names that we didn't hear mentioned was the name of the very distinguished English mathematician, George Temple. George Temple was the professor of mathematics at Oxford until his retirement recently, and before that was professor of mathematics at King's College London. He was interesting to me in that he started his life as a laboratory assistant at Birkbeck College, where I worked at the university. The then secretary of the college, Mr. Troop Horn, took an interest in him and paid for his education. And eventually, as I say, he went on to be the professor of mathematics at Oxford. The reason for mentioning his name was that he was, I believe, the originator of the method of steepest descents, from which conjugate gradients derived, and his classical paper was written in 1939. I was most interested in the remarks both by Maurice Wilks and by Wilkie this morning on the subject of Turing, who of course I knew moderately well, as far as anybody not working with him could know. The thing which sticks in my mind mostly about Turing, and nil nisi bonum and all the rest of it, but I can't help remarking at one of Maurice Wilkes's colloquia at Cambridge, Turing lecturing, oblivious to the fact that the tail of his shirt was hanging up from the back of his pants. Now, these days that would occasion no comment, but I do remember that. I remember a most obscure dissertation on a subject I've now forgotten, but Douglas Hartree saying at the end, and I don't think Turing took any offence at it, he said, it's a funny thing that Turing has the happy knack of making the simplest thing sound difficult. And that was one of the remarks I've always treasured. Hartree was a very well-intentioned soul, but he did say that of Turing. Getting around about 1947, and I give a systematic account of our own work shortly, but these are remarks which were prompted by things that said. When I first heard about the ENIAC, which was in 1946, I did some sums as well on reliability statistics, and we'd come to the conclusion that we'd heard that ENIAC was 50% reliable. Now, obviously that figure was wrong, but that's what we were told. And the cynical remark made by some acquaintances in the engineering field that I knew was, yes, that it worked every other microsecond, which of course would probably mean that it didn't work at all. That is just a scurrilous remark, and you can ignore it. In 1946, I visited the States to look at all of the computing facilities then to be seen and to choose which particular group I wanted to work with, and I shall tell you later that it was the von Neumann group. But among other things, I did see the BINAC. I was interested in the diffuse remarks about BINAC. I discovered nothing about its mode of operation. I did see it. I asked what it did, and I was told by the man who was showing me around, whose name I've now forgotten, that it did nothing, but that it was very valuable to the company that had bought it because it impressed the customers that they were with it, and they were very happy with it. Perhaps somebody else would like to comment on whether that was a scurrilous remark as well. Question was raised in discussion that Pitts and McCulloch, in their neural theories, sadly slightly forgotten and tarnished these days, suggested to von Neumann logical symbols. as indeed did the mercury delay line, which hasn't been remarked so far. Von Neumann resembled to the alpha rhythm in the brain. He thought that because the brain exhibited this phenomenon of alpha rhythm, that showed, as a curious example of an incorrect argument from a distinguished mathematical logician, that showed that because the brain had an alpha rhythm, that the brain was in fact a delay line store. I'm not sure that he enunciated it in those terms, but that was certainly the impression I got. He did, in my view at least, from conversations with him in 46 and of course much more extensively in 47, rely on these notions in the design of his machines. I think I would take issue with some of the suggestions that were made that the logical symbols were inappropriate in the computer field because, you have one logical symbol and a bit of electronics added onto it to make it work. That's not strictly true. And in the 50s, I wrote a paper in the Journal of the Institute of Electronic and Radio Engineers on the relationship between logical symbols and electronic elements, which I showed that within certain bounds you could take some of these logical symbols and you could engineer them realistically in terms of a reasonable number of valves. My recollection of the days at Princeton suggested also that some of those considerations were at the back of the minds of the engineers. While I'm reminiscing about Princeton, I want to embarrass Ralph Sloots, who's probably forgotten all about it. But Ralph in those days was a person who used to like making up little rhymes. And he made up two, which I, having seen Ralph here, remembered, more or less accurately, I hope. One of them was a personal one, and the other one wasn't. The personal one was that there was a computer called Booth who said, "By gad and forsooth, to shorten the delay of the high-speed relay, apply a spot of vermouth." I don't think I was noted for spots of vermouth in those days, but I've remembered that with affection. But his other one, which was more appropriate, was this. The Princeton electronic computer sadly needed a tutor. When invited to add, the results were so bad that a child of 2 could refute her. I hope Ralph will forgive me for dredging those out, but I've remembered them ever since. In the early days at London, we had a number of interesting people. At Imperial, it was rather funny that there appeared to be little communication between them. But one of the people there was Kenneth Tucker. Tucker, like other people, has left the field since. His most recent book that I'm aware of was on systems modeling. He's by nature a statistician. But he devised some computing machines, and one of these, his early IC machine, was, I think, the first machine to involve, on the practical level, microprogramming. But the second thing that I remember him more particularly for, and this was borne to my mind rather forcibly last week when I was reviewing a paper for, I think it was Mathematical Reviews, on the multiplication method based on what they seem to have dignified by the name of Booth's algorithm, which I'll say something about later on. But Booth's algorithm effectively gives you a method of multiplying numbers of arbitrary sign in binary scale without taking account of what the sign is before you start. Well, the modern embodiment of that is to take the last 3 digits, which shortens the arithmetic process considerably. I noticed in this paper the usual regrettable tendency of the young to ignore all of the previous work and refer to only papers written in the 1970s. I examined the thesis written by one of Tucker's students, Lehmann, on the 3-digit method, and in fact, the rigorous proof which was given in that thesis, which was in the early 1950s, was in fact the proof which has now been regurgitated in some much more erudite journal this year. I think the referees must have been slipping, but anyway, I did remark on this in my little review of it. One of the sources of inspiration to us, and we must give Morris the greatest credit for this, was the Cambridge Colloquia. I think you suffer in North America from the fact that the country is so big. It's certainly true of Canada. But in those days in the UK, that's the 50s, the late 45s and 46s, 47, 48, we were all lucky enough to be hosted to weekly colloquia up in Maurice Wilkes's laboratory at Cambridge. And there was, as everybody has remarked during these meetings, an extreme exchange of ideas. It would be very difficult to say whose idea was which. We were all talking about things, we were all excited about them. I remember, for example, Tom Gold, who's now defected to the United States and is one of the proponents of the modern theories of the universe, talking to me about delay lines. I also remember Tom giving me a circuit for a foolproof amplifier. And I remember trying the amplifier, and it certainly wasn't foolproof because it didn't work at all. I just wondered whether he just wanted to dispose of the opposition, but I don't think that was in the nature of Tom. He didn't. Just to show that one's impartial in these things, later on from Dickie Schneider at Princeton, I also had a circuit for a binary counter. which he assured me was much better than mine. There was a difference, that mine worked and his never did. But that was in the nature of things. If you're interested historically in where one got one's ideas from, where I, for example, learnt about radar, I give total credit to the MIT Radar Handbook, which is one of the nicest written books, and if you transpose it into transistor terms these days, or I suppose into ICs, it is one of the nicest introductions to pulse techniques that I know. I wonder if the NPL people use that book. It really was quite excellent. Well, now to get nearer to what I'm really going to talk about, which is development of computers at London, I should perhaps remark that I went to the United States in '46. I'd been working on a number of computers, and I'll show pictures of them in a moment. I'd come to the conclusion, having heard of the work going on in the States about the application of electronics and of stored programs and so on from Douglas Hartree, I'd come to the conclusion I must visit the source of inspiration and come here to see for myself. Bernal, who was a friend of, among other people, Bush's, but also of the Rockefeller Foundation people, engineered a trip in days when it was very difficult to make a trip. I know that I was apprehensive until I got on board the boat that I'd either get bumped from the boat for a VIP, or perhaps get bumped because the Bank of England wouldn't give us the dollars, which was the real problem in those days. I've never forgotten going to the headquarters of the Bank of England with a piece of paper, penetrating to the relevant place to get the signature. And the man looked at me and he said, "But you can't be here." And I said, "What do you mean I can't be here? I am here." He said, "But you can't be here, the public aren't allowed in." Anyway, I got my piece of paper signed and I did in fact get to the United States. I visited very extensively. I visited Harvard and MIT. I visited the Eckert-Mauchly group. I visited von Neumann. I went across to the West Coast to talk to Linus Pauling, because I'd been told that there were good things in computers on the West Coast. The only thing I saw was a Chinese bank, I think it was in San Francisco, where they were using the abacus. I thought that was really funny at that time, and I suspect it was a sales gimmick, and that was until I went to Moscow in the 1960s. And there I discovered that that's the method of computation, or was the method of computation used everywhere. So I had to get some expenses paid at Moscow University, and there was a large lady with an enormous double abacus with a circle cut out of it to fit her tongue. I think there's probably a word for machines of that sort, but anyway. After the trip to the States, I had to resolve in my own mind the question of where I'd like to work. And after very little thought, I decided that I wanted to work with the von Neumann group. I said a few minutes ago that to Brian Randall that I wasn't going to be obnoxious today, as I tend to be sometimes, and I won't be. What I would have liked to have done was to tell you why I chose von Neumann. But unfortunately, the reason that I chose von Neumann, whilst entirely positive as far as Johnny was concerned, was almost entirely negative as far as everybody else was concerned. So that if I were to mention the specifics, it might give rise to complaint and argument. Suffice it to say that I did decide to go and work with Johnny, and this is a decision which I never regretted. During the early days of my own thoughts on the design of machines, I'd come to some conclusions. Of course, one all knew about storage. I had done an analysis, somewhat in the von Neumann manner, but not in terms of symbolic logic, but in terms of engineering pragmatic reality. And for example, in saying that one needed a store, it seemed to me fairly obvious that no store which was evanescent, that is, in which the information disappeared if you turned the power off, or if somebody blew at it or short-circuited it, was going to be much good. And for this reason, enumerating the physical phenomena which were available at that time, I came to the conclusion that the only valid store was based on magnetism. And for this reason, conceived the notion of the magnetic store. Now, before I went to work with Johnny, I in fact started on getting a patent. And I may say that personally I was uninterested in patents. I'd not be standing here now. I'd be on a yacht in the Caribbean or something, a multimillionaire, if I'd been more conscious of it. But in '46, on the spur of John Wilson, who supported most of my work, and John Wilson was the Director of Research at the British Rubber Producers Research Association. He's still alive, although a very sick man. He's in his 80s, but I pay tribute to him as the person who supported my own work to a greater extent than anybody else. But John Wilson insisted that as a sort of quid pro quo for the Rubber Producers Research Association, they should be allowed to patent some things which we did. And among the other objects written in the first patent was a thing which I called the disk store. And the disk store consisted of a paper disk coated with a magnetic oxide suspension. It was a paper disk because the material that was then available came from a thing called the Mailer voice recorder, marketed by the Brush Corporation in the United States. The disk was to spin about a vertical axis, heads were to be in proximity to it, and the spacing was to be governed by the Bernoulli effect. So in effect, you see, you have the floppy disk invented in 1946. The only trouble was that the floppy disk didn't work. When you spun the disks at the right speed, the Bernoulli effect seemed to have very little validity, and the disks rapidly tore themselves to pieces. So whilst it was in the patent application, I didn't think much of the notion. I was thinking more about solid media like magnetic drums. But if only I'd got that patent, I could now hold somebody up to ransom for floppy disks, and I would be earning a nice lot of money. But anyway, suffice it to say that I did conceive that the magnetic phenomena were the only ones worth working on, and that was something which I worked at consistently for practically the whole of my involvement with computing machines. We heard this morning a lot of talk about the merits of odd coding systems. And one of the things that I recognized right away was that magnetic storage, because we had a mechanically rotating drum, would be very slow compared with the machines that Maurice Works, for example, had. A millisecond was the right sort of time. If you used one address coding, you had to wait a complete cycle for the information to come back. With a drum, the time was a 50th of a second, and that wasn't terribly impressive, particularly in view of the arithmetic unit using relays, which I devised later on, which should do an addition in a millisecond. It's not much use having an electronic store, which was 50 times slower than the basic element of the arithmetic unit. But taking account of this, I, unconsciously I suppose, devised a method of coding which you can call two-address coding or 1+1 or what have you. But it's very similar to Turing's idea, except that with the magnetic storage drum you have some advantages. And the coding system simply involved that you wrote in successive words of the drum two-address instructions. And an instruction might, for example, say, in position 1, add position 2 into the accumulator and go to position 3, which might say add position 4 and go to 5 and so on. As was remarked over the ACE projects this morning, in principle this might give you a nice increase in speed. In our case as well, 16 times the speed of the basic unit. In practice, of course, it didn't quite work out that way. The advantage of the drum was that at least it was simple to operate that type of 1+1 address program. And in fact, all of the machines which you'll see and for which I was responsible used precisely that particular technique. It was also about this time that I decided that there was only one way to retrieve information from a drum, and that was to use a clock track. And I thought this was such an obvious idea that it wasn't worth even telling anybody about. But I discovered many years later that people did think that the invention of the clock track was perhaps a valuable invention. But we had that right from the beginning. It was about the only way of doing it that I saw as being reasonable. I remember at Princeton, where Julian Bigelow and his cohorts were involved with the magnetic wire auxiliary store on the Institute machine, the complexities involved in trying to retrieve information with a self-clocking device. I shuddered to think of the difficulties of doing that, and I was delighted that I'd adopted the clock track method of operation. I could remark also, in conjunction with Maurice's talk this morning, that we had certain advantages in using the drum. One of them was that when you put information on the drum, you could put on your initial instructions, so that we didn't, in fact, need to have a uniselector for doing it. And that was a rather pleasing function. There were some difficulties, however, because in the first machine, my colleagues used to take enormous delight in coming up with a large magnet in their pockets and wiping the drum off. Now, it didn't matter that they wiped off the input routine, but they also wiped off the clock track. And that was a much more serious business, because putting the clock track on in those days, we did with a dividing head and a device which applied a battery effectively to a recording head. But when we discovered this nasty trick of our well-intentioned colleagues, we built a little electronic circuit which put clock tracks on, and later on we engraved them on the drums. There's another point, of course, that in the type of two-address machine that we had, we got over initial problems altogether later on when we had an input by having on the tape an indication with each group of words as to where those words went on the drum. Now, you didn't have to use this, but there was a special input instruction which allowed you to do it so that you could input data to a machine which was basically memory clear. And that was a certain advantage. And then finally, and I'll get on to the subject of the talk briefly, I was interested in the vector operations on the old ACE computer. later on, to speed up multiplication, we had on the Apex series of machines a thing called a vector track. And this vector track did give us a facility for adding part or whole of a track into part or whole of another track. And although I never used this particular instruction except to speed up multiplication, it was in fact, I think, just about the same as that one had on the ARC machine, the ACE machine. Now finally, another little story, which no doubt for reasons of modesty, Wilkinson didn't tell us this morning. I was at the third of the meetings which revealed the ACE pilot to the public. But I remember particularly the publicity attaching to the first of these demonstrations to the press. And the press man concerned had submitted to the ACE to find whether it was a prime or non-prime or what its factors were, a number such as, and I won't vouch for the number, I didn't note it down, but a number like 321, a 6-decimal digit number. And immediately Wilkinson said, oh yes, that's got a factor 321. And this appeared in the London newspapers, at least, under mathematician faster than electronic computer. I don't know whether Wilkie's forgotten that, but I certainly haven't. Well, now enough of the random remarks. I'll get down to the meat of this matter and try to finish it up quickly. One of the pioneers, who hasn't been mentioned, and you see now I'm slightly disconnected because this has nothing to do with the remarks that have been raised at earlier parts of this conference. One of the pioneers that we ought to remember is a man called E. Williams Phillips, who was an actuary who worked in London in the 1930s and who produced a complete set of designs for a binary machine and had notions of an electronic stored program machine. I was never able to understand what Williams Phillips was talking about. He offered us the machine for Birkbeck College. Perhaps unwisely we didn't accept it. We got enough junk from my own machines at the time and I didn't want to add to it. But I think that Williams Phillips should be remembered, and perhaps some other people would like to take up the question of what his contributions were at a time when Konrad Zuse was also working in the field. Well, now perhaps we could have the first slide, please. This is my first expedition into the area of digital computing machines. So electronic engineers never know how to turn the lights off. If they do, nobody can put them on again. This was a machine for finding the value of a Fourier transform. It was built in 1941-42 when I was at the University of Birmingham, and it consists effectively of a roughened surface, a small wheel, something like the wheel used on a planimeter, and a scale calibrated in such a way that if you rotate this device through a particular angle, you in fact put into the counter the cosine of the angle multiplied by the ratio of that distance to the total length of the arm, which you'll see, if you repeat the operation several times, will give you the summation that you want. You calculated that angle by means of a desk calculating machine. Well, that was the first machine that I was responsible for designing. I call it a digital machine because unlike the planimeter, which I suppose displays digits, but anyway in an analog form, this one did have a digital counter on it. And that was built in the 41-42 era. Next one I was concerned with was also digital in a different sense. Could we have the next slide, please? This was a much more grandiose machine to calculate the values of this expression, but with values of x suffix r, y suffix r, and z suffix r, which were input in digital form, and with FRs, which were set in analog form. Effectively, there were 3 levels of settable CAM in this device. They were set by means of a jig, which is not shown in this picture, but in terms of a collection of teeth which are on a wheel here, you could set in X, Y, and Z. Now, by means of an automatic device, this set of cams was raised to 3 different levels to give you the H, the K, and the L, and the whole device was in fact rotated once for each level. And by doing this, one was able to calculate the whole of this expression directly. You multiply by FR by means of a Scottish crosshead, which you can just see up here, and you perform the summation by means of a Kelvin chain. And this is just one unit of a set of 20 which we made. I don't know the extent to which these machines still exist, I certainly have one of the units which was given to me when I left the Rubber Producers Research Association. I must say in all honesty that my interest in this type of mechanical calculation had waned by the time the thing was finished. And as far as I know, it was never set up and used. But that was finished around about 1944. But this time I'd become interested in the field of real digital computation, and I started work on a relay computer. And the next of the slides shows some work done in 45-46. Notice the ubiquitous uniselector, which we've heard about today, a set of push buttons for setting numbers in, and a set of relays and a few semiconductor elements on here. This was the first accumulator which we had, and it would add 2 binary digits to 2 binary digits. And that was the basis of the big machine which we set out to build to mechanize this operation completely. Now, I'm not going to give you a description of the machine, a historical monster. I never bothered to write it up because basically, although we tested it, it too was never used. That was always the trouble with the people who worked in the early days, at least in university labs, that we all got interested in building a new machine rather than finishing off the old one. It wasn't until the funding bodies said, well, look, produce or perish, to paraphrase the more modern expression, that we decided we really would have to finish one. It was in fact said of Charles Babbage that at the end of his life he found himself at the end of a long shed filled with the unfinished remains of his machines. I think that was substantially true, and it might very well have been true of me if the various people who funded me hadn't decided that they wanted one finished. Well, this machine wasn't finished, but that, to my knowledge, was the first binary adder. And I shall tell you a story about adders in a moment. Can we have the next one, please? Here's another little picture. This is some of the people involved in building the whole machine. That is the young lady Xenia Sweeting, and that's my wife, Kathleen Britten, as she then was. I show you this picture because that device was, to my knowledge, the first function table. I'd never heard of function tables at that time, but I did have the requirement that I should be able to get from a single input a binary digital version of a function, specifically in this particular case the sine or cosine function. So I wired this up into what nowadays would be called, perhaps I shouldn't say nowadays, in the Princeton days would have been called a one-many function table. And that is in fact a picture of it. That particular device was finished. It used selenium rectifier stacks and fed the arithmetic unit, which you can see here. That was the full parallel binary arithmetic unit. So the next one, please. Some more work on the same thing. Notice the state of technology in the UK. Maurice didn't remind us of this morning, but I suspect we must have visited the same junk shop to get our punches. You notice the same old model that you had with the electromagnet driving the punching device on the left-hand side. I think Maurice must have had a better one than mine. That machine was a total disaster. That was a picture taken when we were all fondly writing some tapes for the machine. Next one, please. I show you this one because this has another form of function table in it. This is in fact a schematic of the structure factor calculator. Here it is, the sigma of some very complex function. I want to draw your attention only to one feature of this machine, and that feature is the function table which we have here. This is a many-one function table constructed with relays, what we would nowadays call a tree. You notice there are a number of levels, and you can produce a number of outputs. And actually, the interesting thing here is that it was not only a many-one, but it was also one-many. So having decided which particular binary input code you had, in terms of that particular code, you could actuate one of a number of output stages. And that was the thing which we'd been working on in the period 55-56. Next one, please. Oh, that's another view of the diode matrix function table. Slightly closer view, you can just see it. And bits of the arithmetic unit on the other side. Next. I apologize for this slide, but early slides of Princeton are somewhat lacking. I haven't got the knack of photography in those days, but I did take a picture of this particular unit, which was, as far as my notes tell me, a 10-digit parallel accumulator. The picture was taken in March or April 1967. It was designed to test the speed of propagation carry, because in those days any propagation carry which took more than a fraction of a microsecond wasn't judged to be worthwhile. But that was the arithmetic unit prototype at Princeton. It was at least in part designed by Willis Ware, who's with us today, and by Dickie Schneider, who is not and who seems to have dropped out of the business. Could we have the next one, please? Here's another picture of one of Schneider's monsters on the bench. This was an interesting one in that, as far as I can remember it, it achieved digital addition by some very complicated algorithm involving the analog addition and subtraction of voltages. And also, as far as I remember, it didn't work very well. You notice the primitive cooling device on the end of the slide. Next one, please. Well, as he couldn't be here, and we've lost touch with him, this is Dickie Schneider, taken at the Princeton boat race in 1947. I can't remember who Princeton raced against, but they used to have this event every year. There he is in a characteristic attitude. I was interested in X-ray and protein work at that time, and the gentleman over here is a man called Chris Krieser, who was a molecular biologist in those days. But anyway, that's Dick Schneider, and he's, I believe, forgotten in the annals of computing these days, but certainly not in my mind. He was the most interesting character with whom to talk. Now could I have the next one, please? This is some notes taken from some diaries which I looked out for the conference we held 3 years ago in London. This gives a chronology of 1947 and 1948. And some of these notes were written at Princeton, some back in the UK. For example, Tuesday, March the 18th, we were considering the possibility of a new memory organ. This was an interesting device. The memory organ at that time was what later got called the iron nail memory. And I talked about this at one time in Princeton. It used the magnetic remnant properties of Swedish iron. The only Swedish iron we had was nails, which weren't the best form of Swedish iron, in order to store information. I did make a 2x2 matrix using this material, which just about worked, but obviously it just about wasn't enough to make a large store. But that was the earliest reference which we had to the memory organ. Then we had another one on March the 19th. You can see that the brain was working at that time, a wire and paper memory. This was a read-only memory in which, to a large sheet of paper, one applied 2 grids of conductors. You apply a large potential to 2 conductors, one in each direction, perforate a hole in the paper, which in the concept involved would have a non-infinite conductivity, and you could therefore use this as a type of function table. But in effect, it was a read-only memory. We made one of those, and it worked on a limited scale, but we never took it any further. Thursday, October the 23rd, we got back to England, by the way, in the middle. We got our first shift register working. Wednesday, November the 12th, we had a coincidence sensor working. The coincidence sensor was the device which enabled us to compare the position in which a magnetic drum found itself with the position of the word which we desired to locate on the drum. Once you found the position, you can then emit the word with a standard set of gating. And as I say, we got the circuit working on Wednesday, November the 12th. On November the 22nd, we were working on pole piece design for some reason, which now escapes me. And on Tuesday, December the 16th, we got a full accumulator working. Then, proceeding to 1948, we got the memory working in toto on the 1st. We saw F.C. Williams at Manchester on the 5th, and I remember exchanging a device called a mag slip. I can't remember why I wanted a mag slip, but exchanging a mag slip for a magnetic recording head, which Tom Kilburn, who was talking to us, took back with great glee. Here we've got a meeting with O'Donnell Livesey with respect to the patents on ARC. He's the patent agent that I told you we had a certain amount of difficulties with, and we ever got any patents on anything. Thursday, February the 19th, we got 256 pulses on. That's a bit of jargon. That is 256 words of drum storage on a 2-inch diameter nickel-plated drum. I'll show you a picture of that in a moment. On May the 12th, work on the machine was debugged completely, and Sir William Palmer and Mr. Dickey, who were members of the board of British Rubber Producers Research Association, I put impressed. My recollection of that meeting was quite different. They came to see it, and I've never forgotten the event, because as this distinguished delegation, which was Sir William Palmer, Mr. Dickey, and my old boss at Birmingham, Sir Norman Howarth, Nobel Prize winner, as they came into the lab, we'd been having some difficulties with the machine. I was working behind it with a screwdriver. There was a blinding flash, the lights went out, and the screwdriver more or less vaporized. Being a relay arithmetic unit, there was a lot of current available. But I put down impressed. I must have been slipping at the time. And then finally, on May the 23rd, Warren Weaver and Gerard Pomeratt came to Welland to have a look at the machine, and on the basis of that gave us some more money. But that was just a chronology which I thought might interest you. If we go to the next one, I'll show you the original store. It consisted of a 2-inch diameter, 2-inch long brass cylinder plated with about 1/1000th of an inch of nickel, driven, as befits all good British science of that period, by a small electric motor bought in war surplus and a piece of string. The device is still in the Science Museum in London, and I believe can be seen, although I haven't seen it. The piece of string was given with it. I hope they've preserved it. You can see the sort of tube that we used. These horrible things were things called VR102s. They were sort of 6SM7 in a single envelope, but with one of the grids brought out to a top cap. These tubes, which are on the amplifier type chassis, were EF50s, which was the type of pentode that we used in those days. I should at this point explain to you that the ARC machine, which was the first one we built, had its logic designed whilst at Princeton. Now, I recognized that there were certain problems to be solved, and that the major problem, in my view, was the design of a store. I believed that the Princeton people could be relied on to produce fast arithmetic units, although there were undoubted difficulties which they were finding. But I did believe that the storage problem needed attacking, and that was the one I was going to devote myself to. I'd acquired a fair amount of skill from the previous machines in designing relay circuits, so I took the von Neumann Princeton design and parallel design, and I turned this into a relay design. I designed it whilst I was at Princeton. It took about a week, and as a result of this, we put it together and it worked first go, which you should be able to do with relays. It was a 21-bit parallel machine, complete with full multiplier for arbitrary signed binary numbers and a von Neumann divider, which would divide with arbitrary signed numbers, and of course add a subtractor and the other things. But the relay unit was, the arithmetic unit was relay. The storage unit, which we were to put with it, was in fact this drum unit, and you can see it down here. So the ARC machine was relay arithmetic plus drum store. And that was the one that I referred to as being working at that time. Next slide, please. This was the next drum that we built, a full-scale drum, with a large number of heads. That was described later in a publication. It was used in several machines afterwards, because I would take one machine, cannibalize it, perhaps resuscitate the original, but certainly use the bits and pieces for the next one. And that was the first full-scale working model drum. The first one was the prototype for the parallel machine, and this was another one used for the serial machine. I think that's also in the Science Museum if anybody ever wants to see it. Next one, please. This is the relay arithmetic unit and the control. Arithmetic unit, 21 identical chassis with the accumulators and all the rest of the stuff on them, and the control unit, which is over there. The control followed exactly the von Neumann Princeton design. There's nothing original about it except the circuitry. The concept of it was exactly von Neumann's concept. Next one, please. This is in fact the control circuit of the Mark II control circuit, I notice, 1947, so it actually got the date on it. I won't bother to go into the design of it, but if any of you are interested, it'll be in the written version of this talk, and one could probably give an explanation. Next one, please. We've had a lot of conversations in the last 2 days on the subject of whether you design your programming system before the machine, during the machine, or after the machine. Well, whilst I was at Princeton, my wife did the programming side and wrote a little manual called Coding for ARC, and this is one of the first programs ever written to it. There's a photograph from it. Apparently it's a program to calculate sigma an x to the nth. There's a flow diagram. Personally, I agree. I don't think much of flow diagrams. I don't think I've ever written one in my life. But anyway, there was one. That was the way to do it. And then there was a sort of schematic program, and finally a detailed assignation of storage. But we did, in fact, work on those things. And my recollection certainly is that subroutines were well understood and the manipulation of them were well understood at Princeton in 1947. Next one, please. Oh, this is another historical one. I mentioned in the little chronology the visit of Pomeratt and Weaver from the Rockefeller Foundation. This is a picture of them. That is Warren Weaver. Sorry, that's Warren Weaver. Can't see them well here. That's Gerard Pomeratt. Weaver, interestingly enough, was the teacher of Howard Aiken. Weaver was professor of electrical engineering, I think, at Chicago originally, and Aiken was one of his students. He spoke often of Aiken. Pomeratt was a bureaucrat, and they're both, of course, now long retired. But that was when they visited our lab, 52 in Rodwell in Garden City in 1948. Next one, please. I was interested in Konrad Zuse's version of a mechanical store. When we took the store off the arc, remember it was relay arithmetic unit and magnetic store, when we took the store off the arc to put onto the next machine, which was SEC, Simple Electronic Computer, we didn't want to abandon arc. My father, who was a mechanical engineer, designed a mechanical analog of the drum store, which you see here. And this worked for a number of years. What in fact happens is that it is literally a drum, about 2 inches in diameter. There are a number of slots in it. I imagine 21. I can't actually count them. Could be 32, but I think probably 21. On each of these is a bead or insulating segment which can be moved by means of these mechanisms into one of two positions. Underneath the writing mechanism is a reading mechanism, so that you can read whether or not an insulating bead has been moved into one of its two possible positions. Now you saw the size of Zuse's thing. This thing was exactly the same size as a magnetic drum. It was about 1 foot long, about 2 inches in diameter. And it stored, I'd have to count these, but my recollection is about 128, 21 binary digit numbers. It's quite slow, of course. This didn't run at 3,000 RPM. It ran at a quite moderate speed of about 5 revolutions get this right, about 60 revolutions a minute, sorry. And it had the advantage that you could stop it in between words, and that's a very great advantage, because not only is it a permanent store, but you can stop it and wait to go on to the next instruction in the event that your instruction takes more than the time that the drum would take in turning to the next position. But it shows that you can do things mechanically. I think there's a lot to be said for mechanism, although perhaps not in these days of integrated circuits. Next one, please. This is a picture of the SEC, Simple Electronic Computer. We took the ARC store, which you see here. We connected it to a full electronic arithmetic unit, and the young man who was my research student at that time, Norbert Kitz, is seen working on it. The SEC machine had only a partial arithmetic unit. It would add and subtract. It wouldn't, in fact, multiply. We did it, we built it, to test out the whole assemblage of control and shift registers and so on. We went on from SEC to build the next machine. Now, next one, please. Yeah. We redesigned the drums, by the way, in the meanwhile, too. This is the next version of drum, 256 words, each of 32 binary digits, with a clock track, which you can just about see on the top of it. We'd separated the words. In the old machines, you had to count to find where you were in the clock, and you had to discriminate between digits and spaces. In this machine, we used spaces in between the clock and an auxiliary and second clock track to locate the particular word that we were interested in. The drum ran at any speed up to 6,000 RPM. Mostly we ran these at 3,000 RPM, which was convenient, and this was the store for the first set of Apex machines. We later expanded it to 8,000 words in another drum, which I'll show you later. Next one, please. This is a schematic of the Apex machine. Unfortunately, you can't read the slide to do the count, or I can't from here. I brought it along and we'll put it in the record because it had a count of the number of tubes. You can see here, hot tubes 289, germanium diodes 353, and selenium rectifiers 126. And the whole machine was about 46 or 48 inches in this direction and about 6 feet high. Here's a picture of the drum on the end in schematic form. There was a special type of divider which we projected. One of the troubles with a magnetic drum was to try to produce some immediate access storage. And the way in which I did that was twofold. In the first version, you write the same word in all 32 positions around the drum, and then, of course, the word is available anytime you want to use it, and you can use it in multiplication and division. The second version was to have 32 heads mounted equally spaced around the drum and have a little circuit which selected which head you wanted. This gives you 32 words of immediate access for one track. And the logic of that is shown up in the right-hand corner. Next one, please. This is the final Apex drum, 8,196 words. It's 10 inches long and about 8 inches in diameter. My father manufactured a large number of these things, many of which came to the States. I suppose some of them caused trouble, but I must say that we had one which ran for about 10 years, and we didn't even clean the dirt out of it. So obviously they would work under reasonable conditions. Next one, please. This is a picture of the Apex machine. You can see one of the big drums on the bottom. This is Hilary Stinton, who was an engineer I had at that time. We'd improved our teleprinter equipment, and that was the input-output console. That was a picture taken at Birkbeck College in 1952. Next one, please. I'm not going to describe these in detail, but this was the instruction code of Apex, starting with the stop instruction, as it might be conceived totally appropriate. I show this for one reason only. When we designed machines, we arranged that each higher machine in sequence had a code which was compatible with lower machines in sequence. So the ARC machine had a code which was compatible with SEC, except of course that SEC didn't have a multiplier and divider, and the Apex machine was compatible with everything we'd ever done before. And the later machines, the M2s and the M3s, were compatible with these. And I think there's a great advantage in doing that. But of course, when you've only got something like 16 instructions, actually 32 positions available for instructions, it's perhaps easier to do that than when you've got 100. Next one, please. We're getting to the end now. A very dingy color slide. This was the machine MAC, which we had eventually at Birkbeck College. A very pleasant machine to work with, very, very small, nice and compact, extremely reliable. I don't know what happened to that machine. I suppose it got tossed out when I left the college. But that was the lab. Notice the harking back to Princeton days. This particular slide was 1955, but the cooling was primitive. It was an old fan mounted on a stool. In fact, it wasn't even a decent fan. I remember the engineers knocking up the cage to prevent catching their fingers in the blades. We couldn't afford to buy proper fans. But there's the machine, and that's the sort of programming material we had with it. Next one, please. That is a machine which we called M2, and I made a number of these. Used to keep the lab going by making one and selling it to somebody. The M2 basically followed Apex design, except that it had a somewhat different drum, the one with the track, which would store 32 words of immediate access storage, a flatter drum and shorter than the other ones. It also ran at higher speed. Tape reader, our own design, and a tape punch, 100 a second tape punch, which we also designed in the lab and which we manufactured for some time. I show you this machine. This picture was taken at the University of Saskatchewan. I brought one of these over with me. We built a transistorized version of it in 1972-3, and I gave this machine then to Moose Jaw Technical Institute. My understanding 2 years ago was that it's still there and working. So if any of you want to see what a 1950 type machine looks like, and you don't want to leave this continent, you could go to Moose Jaw Tech. I've never been there, but you could go and see if you ever want to. Well, that was the M2. And I think that's probably the last slide. Am I right? Yeah, last one. Thank you. Well, that roughly is the history of my own involvement in computing machines. As you know, I've become involved in somewhat different things nowadays, although I still try to keep an interest in the field. We just recently have connected a small PDP-8 type machine to a scanning electron microscope for work on the recognition of chromosome abnormalities, which is a field I've been interested in for some time. My current interests are more in the applications of computers in the biomedical field. But I congratulate those people who've come after us, and particularly the people who designed the little baby computers, so that I can now do rather more than I did with ARC and SEC with a machine which I can take around in my pocket. Thank you.
Very much.
Gone on too long.
We've time for a few questions.
Brainerd of the Moore School of the University of Pennsylvania. I would like to make a comment on several of the statements made and then to raise a question. I trust I jotted this down properly when verbatim, that the speaker said, "I do not know whether MIT would have created a digital computer at that time or not." Let me say that in my opinion, and according to such criteria as some of us have gotten up, the answer is no. This question has arisen often. It seems to be almost automatic. Why didn't MIT do it? For very good reasons. Of course, it was tied up in digital. But I knew Caldwell up there very well, but I also knew others in the EE faculty, and they were all, and we have good reasons for believing this as far as ENIAC is concerned, they were all believed that the digital machine was impractical at the time. Another question I'd like to ask is the Dick Snyder who's being referred to here. At Princeton, there are the RCA laboratories of Princeton, New Jersey, the Princeton University of Princeton, New Jersey, and the Institute for Advanced Study of Princeton, New Jersey, no one of which is connected with the other. Dick Snyder, that I knew, came down to the Moore School from RCA very shortly after the war, a year or so. He immediately showed me his binary counter made up of magnetic units. So the statement it wasn't working at the time is probably true, but I'm not sure that it meant very much because he had it going very quickly. Question I'd like to ask is, there was a reference to the MIT Pulse Handbook. I'd like to know what that is. I followed most of the publications at that time, and that doesn't ring a bell with me.
Well, the book concerned was called the MIT Radar Handbook, and it was, in those days, a large book with a blue cover.
Oh, you mean the book that was entitled Ultra-High Frequency Techniques?
No, that was a different one. That was a thinner book. No, this was a book about 2 inches thick.
That's what I'm talking about.
The Ultra-High Frequency Technique was a totally different book. I know that one as well. That wasn't anywhere near as good. Incidentally, I would agree with you on the Bush-Caldwell thing. I think we must have got a different Schneider, because Dick Schneider, as far as I know, didn't work with magnetic cores, and the counter I was referring to was a hot tube counter.
James Tuck, Los Alamos. I'm so glad you mentioned that ancient computer, the abacus. I think it's the first time it's been mentioned. My first contact with the abacus was with Nick Metropolis's Maniac. I remember just by the door there was a glass-fronted case. Under it said, "In case of emergency, break glass." And you know what was inside.
Jan Reichman, RCA. Since Dick Snyder is being mentioned, he happened to be a colleague of mine at RCA Laboratories, and the arithmetic unit that he mentioned was developed at the laboratory. It was a DC coupled circuit, and it was a set of DC voltages, 2 sets of DC voltages for the add and the organ, and the sum appeared as another set of DC voltages. It was also in those days that we developed resistive matrix memory, and all of these things, to just set the dates right, were made in 1939, 1940, before any of the present were underway.
Yes, I think I should agree. The resistive memory I was talking about was the one with burned holes in paper. The resistive matrix was quite well known. It was state of the art in '46, which is the first time I was involved with it. I would agree with you. I should perhaps just tell a little story, which doesn't take a moment, connected to some extent with RCA. I think it was on the occasion when I visited Jan Reichmann with Zworykin, who was at that time, I suppose, the big white chief. I was taken home for some reason by Zworykin in his car, and being a simpleton from the UK, I hadn't recognized the great advantages of US technology. We drove up to Zworykin's home, and he pushed the button of the horn on his car, and mysteriously the doors opened, and he drove into his garage, and then we got out, and I said, "Well, this is wonderful. I suppose that's all automatic, you see." And he said, "Well, no, I'll tell you, as you're one of us." I said, "Oh, yeah, what?" And he called, he beckoned, and a large gentleman, I suppose it was his butler or something, appeared from the side, and he said, "No, he has to stand there when I have visitors and open the door when they turn up."
Well, thank you very much.
Would you like to disencumber me?